Assalamu alaikum everyone. I welcome you all to the lecture 5 of this design series. Today inshallah we are going to discuss the design of cold form steel purlins. Before going any further, I want to clarify a few things. So this was our main plan, the roof plan. The purlins can be arranged in two ways. Number one is this, that the purlins usually rest on top of the rafter. If this is our rafter and these are the purlins, so usually in most of the cases the purlins are resting over top of these rafters, but in some cases it might be the case that the purlins are connected to the web of the rafter. If you see here, number 2 point, this one, sometimes it happens that the purlins and the top level of the rafter is same, so in that case the purlins are connected to the web of the rafter. Let's see what are the advantages and disadvantages of using both these arrangements. If you look at section B, there are two cases. First case is when purlins are resting on top. This is the preferable case for a couple of reasons. The first reason is that if purlin is resting on top, then we can easily provide the cross bracing across rafters. If I draw my bracing on plan, the bracing can come at the web portion of the rafter like this. So it is easy. If we want to brace the structure or if bracing is required, then it can be easily done in case when the purlins are resting on top of the rafter. Whereas in the second case, this option is not possible because then the bracing will clash with the purlins at these locations. So this is one disadvantage for a second option. Then one big advantage for using this first option is that usually the arrangement is such that if you see this section B, first case, the purlin shown in blue is coming from the left. This is the left purlin, and the one shown in pink or magenta is the right side purlin. So usually the purlins are arranged such that the purlin coming from the left is not stopped at this rafter. Instead, we continue it and it is extended beyond the rafter. Like this dimension, it is 0.6 meter in this case, and similarly the right side purlin is extended beyond the rafter, and the total overlap between these two purlins is 1.2 meter. So in this way the continuity is achieved between purlins, and they behave as a continuous member, just like a continuous beam. So how will the moment diagram be in this case? So in the first case there will be positive moment in the mid span and negative moment at the support location or at the overlap locations. So what advantage does it give? I think most of you already know that when there is positive and negative bending, the section size is reduced, so we can avoid using higher sections when we are arranging our purlins in such a way that they are overlapping at the support regions. So whereas in the second case these purlins are just simply supported and there will be no negative moment at the support, and all the moment will be positive moment, which will result in higher purlin sections. So the first option is preferable, and in I think 90 to 95% of the cases this is followed. I hope you have understood the concept. Then if we look at section A, usually there is some slope. Let's say there is a 5 degrees slope, the rafter is inclined. Similarly, if I zoom in this section here, so if there is 5 degree slope, definitely the purlin will also be inclined at 5 degrees with the vertical axis. If this is the global axis, let's say z axis, then purlin vertical axis will be 5 degrees inclined. So what will happen in this case? Since our loading is vertical, it is gravity loading, the live load and dead load is acting downward in the vertical direction. So this loading, and since our purlins axes are inclined, we can call this as a major axis. Major bending will be about axis 2 and minor bending will be about axis 3. So this inclination will cause the bending in both directions, which means there will be major as well as minor bending. So we need to incorporate that and simulate that in our design. We will just, when we will go to the SAP model, we will discuss this there in detail. So without delaying further, let's go to the SAP model. Okay, to design the purlin, I can either make a new model or I can just save this file, save it as purlin. Okay, now before removing any members, I will just show you the loads so you are clear that what loading we need to apply. I will go to display object load assigns area, and here I will check the last option, the dead load. The dead load value on the maximum dead load is 0.5 and the units are kilonewton per meter. Similarly, we can check the live load. The maximum live load is 0.4 kilonewton per meter. So we need to apply these loads when I delete all the rest of the members. I will press F4 and I will just turn on my areas by pressing Ctrl W and unchecking this option. Since I only need the purlin, so I will just deselect this one and delete all the rest of the members. To turn on the grid or to display the grid, the shortcut command is Ctrl D. I will just select this purlin and I will move it to the origin. It doesn't matter, but I just prefer it. Ctrl M is the move command. I will select pick 2 points on model, click on the first point. I want to move it here, click on this point and click on apply. To hide the grids, press Ctrl D. Now we need to apply loads to the purlin. So I will go to assign, frame loads, distributed load, and in the dead we already know the load value was 0.5. Make sure your units are correct, it's kilonewton per meter. Click on apply. Similarly, select again, and the live load value was 0.4. So both my loads are applied. Now I'm going to select the design code. Go to design, cold form steel frame design, view revise preferences. Now by default 3 codes are given in this section. I will just select the second one, LRFD 96. Click on OK. Now to select the design combinations, again go to design, cold form steel design and select design combos. I will keep the original design combinations which we defined earlier, so I will select all these ultimate combinations and click on add. Now to avoid automatic generation of combinations, I will uncheck this option and click on OK. Now to assign the support conditions, I will just select all my joints and go to assign joint restraints. I will uncheck this option, check these two, rotation about 1 and 3, and I will just make this as pin in this direction. We will discuss this arrangement in some later lecture, why I have given this roller support. This is, I'll just briefly discuss here that this arrangement is, or the support conditions are provided to cater for the temperature loads, because usually due to temperature loads there is expansion and contraction in the member. So that's why I've kept it as roller in this direction, whereas fixed in the other direction. So we will discuss this later when we go to the temperature loads. Okay, now our member is ready to be run, so let's press run analysis. Click on run now, and let's check the moment diagram. Press F8, the shortcut command for display forces, and here I will select moment M3 and let's view it on ultimate combination 2. And now you can see I described earlier as well that there will be negative moment at support when we have overlapped the purlins. So this is actually simulating the exact scenario, whereas you can see at the edge or at the corners there is no negative moment because the purlins are stopping at this location. It is not continuing any further. But in case if the purlin is there is some cantilever portion at the end of the structure, so the purlins are going to be extended, and then in that case there will be some negative moment at the ends. So this is okay. Let's run the design. To design, click on design, cold form steel design, start design, check of structure. The shortcut command is shift plus F8 and I will be using that now. Okay, now you can see the utilization ratios are very high. The purlins are failing. It's 2.95 at the edge purlins and 1.02, which means 102% in the center member. So let's check. Okay, here we can see that the utilization is pretty high in the minor axis as well. So what we are going to do is, in the last lecture we discussed one concept of unbraced length ratio. So I want to discuss a similar kind of concept here. If I consider this as 0.1 and this as 0.2, so from this end to this end, this is the purlin span, which means that my purlin is totally unsupported in this length. So in this case the unbraced length ratio is equal to 1. But there is one concept that usually we provide sag rods for the minor bending. Here you can see in this section A, these are the sag rods shown in gray, and these can be mild steel bars or normal threaded rebars which are bolted at the end of the purlins in this arrangement, in this sort of arrangement. So we can check that how many number of sag rods are required. Let's suppose if this is 1 and this is 2 if I provide one sag rod in the middle, then in that case the unbraced length ratio for the minor axis will be 0.5 as discussed earlier. But if we provide two sag rods, then the unbraced length ratio will become 0.33. We have already discussed that how to calculate this unbraced length ratio. So I am going to provide two sag rods in each span. So let us unlock our model. I have selected all my purlins. Go to design, cold form steel design, and view revise overrides. Here the fifth number, it says unbraced length ratio minor. So I am going to edit and modify it as 0.33. Click on OK and let's rerun the analysis. Shift F8 for design. Now you can see by inserting sag rods or simulating that behavior, the utilization ratio has decreased, and now the maximum is 89.4%, so which is within the limits, and the purlins are passing. So this is okay. I would like to incorporate one more thing here. Let's check the extruded view by pressing Ctrl W. Okay, here you can see the vertical axis of the purlin is directly aligned with the vertical global Z axis. So I've discussed earlier that usually there is some slope, 5 degree, 10 degree or 15 degree slope. So To incorporate that in our model, let's just consider 5 degrees slope. So I will select all my purlins, go to assign frame and local axis. Here I will just give 5 degree slope. Now you can see the purlin is slightly inclined at 5 degrees from the vertical axis. So let's see what impact does it bring to the utilization ratios and the design of the member. Shift F8 for the design. Now our by inclination of purlin, since the minor bending has increased a little, so the utilization ratios has increased further from 84% to 94%. So this is still okay and within the range. One more thing, this is actually a conservative design. Usually if I want to simulate the exact behavior, so you can see this 1.2 meter portion has overlap region, which means the thickness of the purlin is doubled in this location. So I can add or define another section and I can just input that here at 1.2 meter length of I can define the section with double the thickness of the purlin, and then it will just simulate the exact behavior. But this is a conservative approach and the section is passing easily, so I think this is okay, and the purlin size which we assigned earlier is good to go. So I think that's all for today's lecture. If you have any queries or comments, you can always comment below and I would be happy to answer you guys. Thank you so much. See you in the next lecture. Take care.